Okay, so I feel like a silent a little bit like that. Alright, so what I want to talk about is some of the calculations I've done over the past few years with some colleagues and students about low-lying zeros of GL2L functions. So for the most part, I'm going to talk about cuspidal new forms. There are a couple of slides here on mass forms. These have been improved a little bit with some work I did with Levent last summer, or maybe 2 summers ago. It's beginning to blend. And I'm not really going to get into that too much. I'm going to concentrate more on the cuspidal new forms, what happens when you try to calculate larger and larger support. And again, that's the main goal. You want to have as large support as possible. The Katz-Sarnak density conjecture is you can use any test function. And if you could use the Dirac delta functional, you could find out what's going on at the central point. You apply this to elliptic curves, you prove Birch limit and Dyer. We are very far away from that. Most families, if we're really lucky, we can get up to -1,1 or a little bit higher. Many families are significantly less than that. -1,1 is extremely important because if you're smaller than that, you can't tell the difference between the 3 different orthogonal flavors. You can tell the difference between the orthogonal flavors, symplectic flavor, and unitary flavor. If you look at the 2-level density, this is one of the main results of my thesis. It's very dinky, but the 2-level is enough to distinguish any of the 5 candidates from each other for arbitrarily small support. Okay, so we're going through some details first. I want to talk a little bit about compound families. And this is joint work with my mathematical brother, Eduardo Dueñas. This paper should have been written a lot earlier in the subject than it was written, because one of the most natural things you can ask is, I have a complicated object, let me break it down into simpler parts and understand those parts. Or conversely, take a bunch of simple parts and put them together, what can I say about the resulting compound structure? And so a very natural question to ask is, if I have 2 families of L functions and I combine them, what can I say about the behavior of this compound family? Is there a way to predict how its zeros should behave based on knowing how the zeros of the constituent families behave? And this was inspired by a specific family that Peter Sarnak gave us to look at, and then we generalized it to try to get an understanding of what's going on in general. So the goal is to try to understand what is the symmetry type. So what should the distribution of zeros look like? Frequently, if you're looking in the function field case, there's something called the monodromy group, and it actually turns out to be one of the classical compact groups. And so if you have a family of L functions, and you have a group that happens to be one of the 5 classical compact groups, it's not so hard to guess which of the 5 classical compact groups probably controls what's going on. Unfortunately, that only happens in the function field case. You don't have that wonderful, here I am, screaming, going on in the number field case. You try to use analogies with the function field case to figure out what it should be. And so, one folklore conjecture in the subject was that the theory of low-lying zeros is essentially a theory of the distribution of signs of the functional equation. If you have a family where all the signs are even, then it has to either be symplectic or SO even. If all the signs are odd, it has to be SO odd. And the belief was, if there is a corresponding family, if you have a family of all even signs, and there's a corresponding family with odd signs that you're forgetting about, then your family is SO even. If there's no corresponding family, then you are symplectic. So if you look at quadratic Dirichlet characters, they all have even functional equations. There's no corresponding family that I've split from. That should be symplectic, and it's symplectic. If you look at cuspidal new forms, I can split the cuspidal new forms by sign. And so I could give you, here's all the cusp forms of weight k level n and even sign. Well, there's also those of weight k level n and odd sign that I'm forgetting about right now. So in terms of what's the behavior of the zeros with even sign, it should be SO even, because there's this corresponding family that I'm just forgetting about. It's an orthogonal family that's been split. And the symplectic family is when there's nothing that you've split from. It turns out that that conjecture is false. There are families where all the signs are even, it's not split from a corresponding family. And it turns out to be SO even. And you have the other cases as well. So let me just briefly go through this. So pi is going to be a cuspidal automorphic representation of GLN. Q pi is the analytic conductor. Think of this as essentially just the generalization of the Riemann zeta function. So the Riemann zeta function, I have all 1s here. If I have a Dirichlet L function with a Dirichlet character, this would be chi of n here for an elliptic curve. I would have essentially something related to the number of solutions modulo p when n is a prime. I use this to build up my L function. The Riemann hypothesis is that all the non-trivial zeros have real part 1/2. I have what's called the Satake parameters, and these coefficients are determined in terms of these parameters. And the number of parameters tells you, what n I'm on for GLN. So the Riemann zeta function, Dirichlet characters, these are on GL1. The elliptic curves, modular forms, holomorphic modular forms, these are coming on GL2. They're going to have 2 terms in their Euler product over here. More generally, I could have n terms. Another way of looking at this, and this will be very important, is that the coefficient here at p to the nth of my L function is the nth moment of these Satake parameters. The most important ones for us are going to be nu equals 1 and nu equals 2, the first and the second moments. You should really be thinking central limit theorem. The universal behavior you see in sums of independent, identically distributed random variables is because things are controlled by the first 2 moments. The higher moments affect the rate of convergence. We're seeing a very similar phenomena going on here. And so anyways, I've got my Satake parameters, I form my L function. This is very similar to the Euler product you have for the Riemann zeta function. And then as we talked about last time, here's my explicit formula. My sum over my scaled zeros of my test function, which has rapid decay, is equal to something nice. This is coming from the gamma factors. Then my Fourier transform of my test function, essentially at the primes. This nu over here, if you want to think of this nu as I have p to the nu. And then I have my Fourier coefficients. It would be wonderful if the conductors were independent of the form, so that when I sum over the family, I could take the family sum, pass it through my test function, and then just bring it to these coefficients and use some kind of averaging formula. If you think about it, then how large I can calculate it, if my function has, the Fourier transform is supported between minus sigma and sigma, p to the nu can be at most q pi to the sigma. If it's q pi to the sigma, then for p to the nu, then I would get sigma log of q pi over log q pi. Okay, I get g hat of sigma. That's just where things break down. That's where it starts to become 0. So this restricts the values of primes we have to study. So because my function has compact support between minus sigma and sigma, I only care about primes such that p to the nu is at most q pi. Okay, so what we decided to do is introduce what we call a symmetry constant. And I never took a class in group theory, so fortunately my level of group theory in fields is just sufficient for this. All right? CL is going to be 0 if the family has unitary symmetry, 1 if it has symplectic, minus 1 if it has orthogonal. And in the Rankin-Selberg convolution, if I take 2 L functions, this is advanced, but you can form a new L function from them. And the Satake parameters of the convolution are related to the Satake parameters of the individual ones. And then sometimes your L function might actually split into the product of 2 other L functions. So this does not mean I take LSF and multiply by LSG. It means I'm forming a new L function from F and G. And I'll talk maybe a little bit more about that later. But the Satake parameters of this convolution is just the product of the Satake parameters. And so what we proved is that, without getting into too much details of what nice means, is if you have nice families of L functions, the symmetry of the convolution is the product of the symmetries. So essentially, whenever you convolve something by symplectic, you don't change anything, because its symmetry constant is just 1. If you convolve something with something that has orthogonal symmetry, you could actually flip. So orthogonal convolved with orthogonal will become symplectic. And the proof of this is actually not so bad. So I actually don't have it, so this is another one. So assuming the conductors in the family are constant, as I said, we can pass the sums through the family, through the test functions to the coefficients of the family. And we have our first order sum, our second order sum, and the highest sums don't really matter. They're going to just be small, assuming we have sufficient decay in the Fourier coefficients. So typically, these coefficients don't grow too rapidly. So I bring my sum over all the elements of my family into here, and I want to understand how large are the first and second. Well, if you remember, these are just the moments. And then it turns out that when you actually evaluate the sum, in all the different families we've looked at, it's always either 0, 1, or minus 1. And in fact, we'll call this unitary symplectic orthogonal. The value of this sum turns out to control what the underlying symmetry is. What this does is it controls essentially how many zeros you have at the central point. What is the rank of the family? We believe that in almost every situation you will ever look at, these averages are 0. There's only one situation we know of where these averages are not 0. Any thoughts? What's a family of elliptic, oops, gave it away. Elliptic curves. So elliptic curves, the Birch-Swinnerton diet conjecture, having families where you force rank at the central point. That's the one situation we know of where these sums will not be 0. And so when we take that in, we can now see why the symmetry of the convolution is the product of the symmetries. So let's look at the Rankin-Selberg convolution of two forms f and g. So the Satake parameter of the convolution is just the product of the Satake parameters. So I want to study this sum. So again, this is very similar to the sum I was studying here when I just had the form f. Now the only thing that changes is rather than having f, I have f cross g, and f cross g is just the product of the two things. Well, since it's the product of the two things, and I sum of all things, it splits into the product of the two different things. And then by the previous slide, this sum is equal to CF, so I get CF times CG. And that's essentially the proof, is it's all being controlled by the second moment of these sums. And it just comes in a very nice multiplicative way. So if we combine two nice families of L functions, we know what's happening. So again, just doing it a little bit more explicitly, here we go, here's this one, here's this one. We just multiply all the different number of forms, and then we're going to just get CF times CG. Okay. Oops, went a little before. Okay, so now let's go into cusp new forms with a little bit more detail. So this is work I did with Chris Hughes at the American Institute of Mathematics back in, I think, 2003. So we've got a bunch of families where we understand what the low-lying zeros are like. So if you've been reading about Little-Sarnak, they concentrate on the one-level density for holomorphic, even-weight k-cuspal new forms of square free level n, and they see orthogonal symmetry. They also look at the symmetric power, and they see symplectic symmetry. Alright, so let's quickly review. So modular form preliminaries. So look at the space of 2 by 2 matrices, integer entries. SL2Z would mean the determinant is 1. And then we can add some additional constraints. We want C to be congruent to 0 mod n. And we'll call n the level. And it turns out if you take two matrices of this form and you multiply them together, then the new resulting matrix will have its lower left corner a multiple of n. This is a 20-second linear algebra calculation. Okay. These matrices have very nice properties. These lead to lots of great things you can do. The way you should view modular forms is these are generalizations of periodic functions. So we know how important periodic functions are. And what's nice about a periodic function is it's invariant under a very nice change of variable. You replace x with x plus 1, we know what goes on. I could have a function that's almost periodic. Maybe if I replace x by x plus 1, I have a very nice transformation as to how it changes a bit. The modular forms are closer to that, in that if I do these very nice change of variables, I understand how it changes. This is where, if you look at the books on modular forms, they'll talk about the fundamental domain for SL2Z. You can take any point in the upper half plane, and by applying these matrices, you can map it into the upper half plane, and you want your function to transform nicely under sending z to z plus 1 and sending z to negative 1 over z. And then any matrix in SL2Z can be written as a combination of such matrices. And so if you know how your function transforms under each of these, you can then figure out how it transforms under SL2Z. Well, instead of forcing it to transform nicely under all of SL2Z, I can restrict and say I only want it to transform nicely under these matrices. So do you think you'll have more or fewer functions if you put in this restriction that it only has to be nice under these matrices?
More.
More. Because now, it's okay if it doesn't work for some values of C. So you would expect, as maybe n grows, that you should have more and more candidates to look at. So we can define a norm, and this is very similar to Professor Stoich's talk yesterday, between two functions. I'll integrate over my fundamental domain, that's what this means, of my function times its complex conjugate, and then this is the measure on that area. And then we have normalized coefficients. There are always difficulties in terms of how you want to normalize things. There are two good normalizations to use. One is to say that the length, the norm of your function is 1. That's very convenient. You basically think of it as a probability distribution. The other normalization is to say that the leading coefficient in your series expansion is 1. it turns out for a lot of the calculations we're doing, it's much easier if the first coefficient is 1. So that means then you have to worry a little bit about then what is the corresponding length or of the function. Well, it's only going to be a scale factor. And so here, what's important? These are the coefficients. This is the L2 norm of the function. And now over here, there are two parts of this that matter. So this is the gamma function. There is the k. This is the weight of the modular form, and that's fixed. The interesting thing here is we have an n. And so we're rescaling the coefficients by something that actually involves where we are. What we're basically doing is we're saying we actually have some knowledge of how these coefficients grow. We're pulling out that growth, and now we're hoping that we will get something that is, it won't be independent of n, but maybe it's going to be bounded. Is we can now compare these things to all be in the same region. So if you think about what we did last time when we talked about random matrix ensembles, we divided the eigenvalues by the square root of n so that they would all be between -1 and 1, no matter what matrix we looked at for the most part. That's essentially what we're doing here. We have known growth rates of these. The growth rates are going to be like n to the k minus 1 over 2. Let's take that known growth rate, and now the hope is that these numbers, maybe these are on the order of 1. Okay. So what we can do is we can look at these complete sums. And so if you think about sums of exponential functions, typically you would expect these things to be maybe small unless m happens to equal n, in which case you get reinforcement. So this is the standard orthogonality arguments you want to make. So if m equals n, we're taking something, we're multiplying it by its complex conjugate. I'd expect that to be large. If m does not equal n, then the hope is that these are essentially perpendicular, and as I sum over everything, it'll be 0. So for those of you who are listening to the benefit stuff and the Fourier stuff earlier, think of it as two exponential functions with different frequencies. And you would expect that integral to be small. We expect something very similar to be going on here. So the Peterson formula is that if I look at this, I get the following. This is a Kloosterman sum. I'm not going to go into that right now. This is a Bessel function. I'm not going to go into that now. That's a mess. And I had the Kronecker delta. So this is 1 if m equals n and 0 otherwise. So the idea is that when I look at this sum, if m equals n, well, I expect to get a huge spike. I expect to get a lot of stuff. And then the hope is that when m does not equal m, that the other stuff is small and controllable. It turns out it's not always small, and it will sometimes contribute. If in certain ranges this can be easy to approximate, but in the regions we're going to want, there is some real movement going on here that's going to be delicate. So if we have our family of cuspal new forms, here's our L function, here's what the explicit formula is going to look like. We have our test function, we sum over the scaled zeros, we sum over all the forms in our family, we divide by the number of forms. This stuff is just coming from the gamma factors in the functional equation. Then we have our first order sum. The second order sum, it turns out it's actually easy to evaluate. The sums at the prime squares. And we're left with just sums over primes. And you sometimes have to worry about, do the primes divide the level or not? It's not that bad to really put these in and remove them. Alright, so we have a square root of p down here. The prime squared had a 1 over p. The prime cubed would have a 1 over p to the 3 halves. We know these numbers are actually bounded. They're bounded by 2. And so once you have p to the 3 halves and higher, the sum over all the primes will actually converge. And in fact, the sum over all the powers will converge as well. That's going to be this error term over here. Unfortunately, 1 over square root of p, that diverges. When you looked at the prime squared, we had log p over p. The sum of log p over p diverges. But we have a little extra stuff, and everything turns out to be okay at the squares. Once we get to the cubes, we're fine. Okay. So again, more preliminary, some Fourier coefficient review. Here's lambda f of n, and we're putting in some of these known weights. There's a nice multiplicativity. Lambda f of n times lambda f of n is equal to lambda f of mn divided by d. And so here d divides m and n. And then for new form of level n, lambda f of n is trivially related to the sign of the form. So the sign of the functional equation is I to the k, that's fixed, mu of n, that's the Mobius function, that's fixed, square root of n, that's fixed. Here's the meat. It's this lambda f of n term. So the coefficient at n is basically telling you, up to just trivial things to add, what the sign of the functional equation is. So this allows us to split into even and odd families by looking at 1 plus or minus epsilon f. So if I multiply something by 1 plus epsilon f, if epsilon f is equal to 1, I multiply by 2, and I just double the contribution. If epsilon f equals negative 1, I've multiplied by 0, and now it's vanished. So if I want to just understand the sum over the even forms, I multiply everything inside by 1 plus epsilon f. Epsilon f is really just multiplying by an extra coefficient here. Alright, so we need a bunch of different sums. We have the Ramanujan sum. You know, this might be very similar to some things you've seen with Gauss sums and stuff like that. Again, there's no way to have information presented quickly and make sense. You have to just really go through the calculations slowly. There's a lot of number theory prerequisites. This is the main result in Evanian-Slidell-Sarnak. This is related to the Klusterman sum, which I mentioned, this S, M, and C from earlier. They expand it. They get Ramanujan sums. They have the Euler-Phi function or torsion function. They have integrals of the Bessel function. They have the test function we're looking at all these different places. And when they do, and all the dust settles, they end up getting a nice formula for this. It's now your test function times very nice things with an error term that's small. And so the idea is Evanian-Slidell-Sarnak figured out how to evaluate these one-level sums. They figured out how to evaluate the Bessel-Klusterman pieces. If the support is small, the contribution from the Bessel-Klusterman piece is small. As the primes get larger, however, it actually kicks in and starts making the contribution. Whoops, went too far. Alright, so here is a quick sketch of the proof of sigma is less than 1. Alright, this is not a great sketch of the proof, it's putting it on one slide. There's far too much for one slide, but this is the 25-second Pomian's version of how the argument works. So you have your Klusterman sum, which is related to an exponential sum where you sum over all d mod q. And so what d bar means is this is the number such that d times d bar is 1 mod q. It's the multiplicative inverse modulo q. We have bounds for the size of the Klusterman sums. So essentially, the Klusterman sums are going to be bounded by the square root of the modulus. And now we have bounds for the Bessel function. And as long as my primes aren't too large, these arguments here won't be too large, so the Bessel function won't be too large. And then we can use the Fourier coefficients to split by sign and just trivially estimate things. So if the support is small, it's not so bad. Okay, if the support is greater than 2, it becomes a little bit harder. Here's another bad sketch of what the proof would be. So we use Dirichlet characters to split up the Klusterman sums. So if you think about what the Klusterman sums are like, we're going to be evaluating this at prime arguments, where we're going to be summing over primes. Well, all that's really going to matter is what is the prime, what is its residue modulo q. So whenever you think about primes with fixed residues, you want to use Dirichlet characters, you want to split things up into primes into arithmetic progressions. And we can then use that to try to get a handle on those Klusterman pieces. We now have integrals of Bessel functions involving stuff like this with arithmetic factors, and then we want to figure out how to handle stuff like this. And this is the big work that Evanian-Slidell-Sarnak did, is they figured out how to handle all of this with the arithmetic sums. And so for what we're going to do for the higher level densities is we're going to try to reduce back and just use their results. Alright, so increasing the support, we have Gauss sums, where if we have a character, we have the character times a times these exponential functions. These sums are going to be most square root of q. This is a general philosophy in mathematics that if you have sums whose values are on the order of 1, and you have q terms, you expect something to be roughly of size square root of q. This is the philosophy of square root cancellation. It's not always the case, but frequently things cancel to around the order of square root. Alright, so a little bit more detail. These are the Klusterman things that come up. We have m squared, where m is going to go from 1 to a small number. We have a product of primes times n. This n is coming from the fact that we're splitting by sign, and so we have to put in this extra factor of lambda f of n. And then we're playing modulus games. We have all these Gauss sums that come. We have a bunch of things like this that we have to bound. Okay. Some people enjoy this. I actually do enjoy this a little bit. A lot of times it gets very frustrating. Alright, what I want to try to do is talk to you about how you do the two-level density. And I really should have probably put in pauses so you don't see the punchline coming in, but I want to get to the punchline fast. how do you handle the two-level density? This is one of the biggest trade-offs you have in mathematics. You want to reduce to something you already know, but sometimes there's a cost for that reduction. So random matrix theory is expecting us to do a two-dimensional number theory calculation. Arrhenius-Lewis-Sonic did the one-dimensional calculation. So option A is to find the two-dimensional analog of what Arrhenius-Lewis-Sonic did. Option B is to take the two-dimensional calculation that we have to do for the two-level density and convert it to a one-level density, to a one-dimensional calculation, and just quote Arrhenius-Lewis-Sonic. We can do this at the cost of some combinatorics. And so the question is, there's no such thing as a free lunch. Where do you want to pay? And it turns out it's just a little bit easier to do some extra combinatorics and not have to try to figure out the arithmetic generalizations of Arrhenius-Lewis-Sonic. So the two-dimensional integral for the two-level density, I have my test functions, I have two different arguments, I have my Bessel function, and I have this integral like this. And the idea is the following change of variables. Let u2 equal x1, x2, let u1 equal x1. I can solve for x1 and x2 in terms of the u's. I calculate the Jacobian, so if you've taken Calc 3, you can now at least say you finally seen the use of this. The Jacobian of this is going to be 1 over u1. And so when I plug this in, it works out beautifully. I get phi hat, the log of u1 over log of r, the log of u2 over u1, times this du1 du2 over u1. What does this look like? What would you use to understand the log of u2 over u1? So we've got the log of a quotient is the difference of the logs. So now let's let w1 be the log of u1 over the log r change variables. We'll get phi hat of w1 log of u2 over log r minus w1 dw1. This is a convolution. So if you remember convolutions from probability, the convolution of f and g, it's the integral of f of t, g of x minus t. This gives you a nice new function. If there are densities, it gives you nice new densities. This gives me a new function. So let's call C2 this integral, the convolution of these. And it's going to be C2 evaluated at the log of u2 over log of r. So this is just the process called convolution. And now, when I substitute back inward, I now get my Bessel function with its nightmare, C2. This is exactly what I had in the one-dimensional calculation. So I've converted my two-dimensional integral to a one-dimensional integral of a new test function. The new test function, I've snuck one of the integrals into it. Sometimes you've seen, maybe in a Calc 3 class, these tricks where the way you evaluate a one-dimensional integral is you make it a two-dimensional integral, and you can use change of variables. This is how you get the area of the Gaussian as 1. You write the integral, and then you switch to polar coordinates. It seems a little strange to take a one-dimensional integral, and the way you solve it is you make it two-dimensional. So you can use different techniques. I have changed things. There is still a second integral. The second integral is now hidden in here. And I have a different test function. And essentially what will happen is the support of this function will be twice the support of phi. Well, that's not so surprising if you think about where things can live. This lives between minus sigma and sigma. So if W1 gets as high as sigma, I'm okay. So if this is as high as sigma, this could be as high as 2 sigma. 2 sigma minus sigma is still sigma. So this function is going to have support twice as large. And this is why the support is going to go down as you look at the n-level densities. The higher density you look at, the smaller window you will be able to do things. If we did it once, we can do it again. If I want to do the 3-level density, I just now have a Jacobian like this, I'll get a 3-fold convolution. And then everything works out beautifully as before. We have all of these formulas from Katz and Sonic for the n-level density. So this is what number theory is supposed to agree with. The problem is my answers no longer look like this. And the reason they no longer look like this is I've changed the integration and I've changed what my test function is. So now we have to do a lot of combinatorics to figure things out. And so I'm going to skip a lot of this. This is going through all the different combinatorics. This is all the different combinatorics, lots of combinatorics, lots of combinatorics. And it's all these games going back and forth, back and forth. Okay. And then even more combinatorics of now how you do things on the random matrix theory side. And so the difficulty here is I need to show that my two answers agree. And so I have to just play all these games going back and forth. Right, so I'm going to stop the recording here.